In this video, I'm going to show you how to do a correlation and regression analysis using R. We're going to use as our example the correlation that we did in the hand computation video. So we have 10 individuals and we've measured them each on their IQ score and also on an arithmetic test. And we want to know if these two variables are related to each other or not. All right, so first thing we're going to do is we're going to create a vector for our variable IQ using the concatenate function, and we enter in our 10 IQ values for our sample, and then we're going to create a second vector for variable arithmetic, and I'm going to use again the concatenate function and enter in the 10 values. Again, these have to line up. So first individual had an IQ score of 105 and their arithmetic score was 15. The second individual had an IQ score of 120 and an arithmetic score of 23, and so on and so forth. All right, so first let's create these two vectors. All right, we can see in our global environment that they exist now. One variable, 10 observations. And if we just want to know what the correlation is, then we use the COR or correlation function. And then in the brackets, the two arguments are just our two variables that we're interested in learning the correlation between. So if we just execute this, we can see that the correlation is 0.518. And you can also see that that's exactly the same as the correlation. Oops. It's exactly the same as the correlation that we had computed in our hand calculations. If we want to know whether this correlation is a statistically significant result, then we're going to use the core test function. And again, we just put in our two variables of interest. If we execute this, we can see, once again, it tells us what the correlation is, 0.518 between these two variables. And we get the results of a t-test, and t is equal to 1.715, 8 degrees of freedom, and a p-value of 0.12, suggesting that it is not a statistically significant result. We also get the 95% confidence interval here, and notice that the confidence interval includes 0, which is another indication that we do not have a significant correlation coefficient. Okay, moving on to the regression part of this analysis. LM is a function that does a linear model of regression. And here we have to identify which one is going to be our x variable and which one is going to be our y variable. And so we have to use that little squiggly that represents the dependent on. So variable A is going to be dependent, the variable arithmetic is going to be dependent on the variable IQ. In other words, this is our y variable, our criterion, and this is our predictor variable, our independent variable x. All right, if we just execute this code, well, we get a little bit of information, but not very much. So similar to the ANOVA, what we're going to do is we're going to take this code and we're going to put it inside of a summary function, right? So this code inside here is exactly the same as line 158. And I've just added the summary function and put it in brackets. If we do this, now we get all the information that we're looking for. So we have the coefficients for our intercept, right? Our value of A is negative 12.62. The slope for our variable IQ is 0.2556. And we have the standard error for our slope, which is 0.1491. And it gives us a t value and a t-test, right? It's doing a hypothesis test comparing the slope to 0, and it's giving us a t value of 1.715, and the probability that is a statistically significant result is 0.125. In other words, it is not a statistically significant result. One thing I would note is that the t value for the slope is 1.715. If we go back up to the correlation, we see that the t-value is 1.715. In fact, they'll always be identical because, at least in simple linear regression, the t-test is exactly the same test when you're looking at the correlation and the slope of the regression line. So if you wanted to write out your regression line, right, it'd be y hat is equal to 0.2556 times x, subtract 12.6234. Also notice that we have a multiple r squared here. 0.26, or almost 27% of all the variability in arithmetic is explained by IQ. Adjusted r squared takes this value and adjusts it depending on the sample size. You wouldn't worry about that too much. And so next, what we also want to do is we want to draw a scatter plot. And so we're going to use the plot function. And again, we're going to enter the variable IQ is going to be our x. So it's going to be entered first. It's going to be the first argument. Variable arithmetic is going to be our y, so it's entered second. And then we have got the main argument here, which defines the title of our graph, which is going to be a scatter plot of relationship between IQ and arithmetic in quotation marks. And we use the xlab argument to define the x-axis label, which is going to be IQ. And ylab defines the y-axis label, which is going to be arithmetic, again, both in quotation marks. And then this argument here, PCH, is going to tell R what kind of data points to include in our scatter plot. So 19 here tells it we want solid black dots. All right, so let's execute this code. And then we see our plot is generated in the bottom right pane. We see it better if we click zoom. All right, and we can see our scatter plots. Each data point represented by a single black dot. Y-axis is arithmetic, x-axis is IQ. Of course, we want to be able to put the regression line on our scatter plot. So we're going to use this function called AB line. And inside of it, we're just going to include the linear model again. Remember, this is exactly the same code as from line 158. When we execute this, we can see that it has been added to our plot. Right? So there's the regression line. If you remember in the hand calculations, we also talked about adding the y-average line. And so the way we're going to do that is we're going to create two vectors, each with two data points. One for our x-axis. And what I'm going to do is the first data point is going to land 2 standard deviations below the mean of x. And the second data point is going to be 2 standard deviations above the mean of x. All right, so the mean of x, if you recall, IQ is x, is 112. The standard deviation is 15.48. So if we multiply 15.48 times 2, we get 29.96. And we subtract that from 112 and we add it to 112. And that gives us 81.04 and 142.96. In other words, it gives us a point down here and a point up here. Now we're going to calculate 2 different y coordinates. One for the average y, so I'm going to call it y-AVG. And if you remember, the y, the average of our y variable, which is arithmetic, was 16. And so both points are going to be 16. And then for the y standard deviation, right, so we can create the standard deviation line. What I'm going to do is the same thing I did to create the x. So I'm going to take 2 standard deviations below arithmetic and 2 standard deviations above. So if the average for arithmetic is 16, the standard deviation is 7.63, we multiply this by 2, subtract it from 16, and add it to 16, and we get these data points, negative 0.74 and 31.26. All right, so I'm going to create these 3 vectors. Right, you can see they have now appeared up in the global environment. And so I'm going to create a line, another line that's going to be added, and the x coordinate is going to be taken from our variable x, and the y coordinate is going to be taken from our vector of y average values, which is just 16. And I'm going to color this red so that we can easily distinguish it from the regression line. All right, so you can see it's been added if we look here, right? So it's got an X point of 81.04 and 16, and up here it's 142.96 and 16, and then it drew a line between the two. Now we'll create the standard deviation line using the lines function again. We're using the same coordinates of x, but now we're going to be using the y standard deviation coordinates. And we're going to color this one blue so that we can, again, easily distinguish it from the other lines. And so now it's been added. All right, so the first point is 81.04 and negative 0.74, right? Somewhere down here below the x-axis here. And the other point is x, 142.96, and the y coordinate is 31.26. So it's way up here, right? It's way up here. And then it draws a line between those 2 points. And so now we can see, again, this is the regression line. This blue one is the standard deviation line. The red one here is the y average. Remember that as the value of r increases, the regression line will approach the standard deviation line. And as r decreases towards 0, the regression line will approach the y average line.